Hello everyone and welcome back to Math 143 Finite Mathematics. In our previous sections, we learn about the Cartesian coordinate system and straight lines. Today, we will build on those ideas and begin studying the linear functions and mathematical models. This section is especially important because it shows how mathematics can be used to describe and solve real-world problems involving business, economics, engineering, and everyday decision making. By the end of this lesson, you should be able to understand mathematical models, define functions, identify domains and range, work with linear functions, model depreciation, construct the cost, revenue, and profit functions, also analyze the demand and supply equations. Okay, then let's begin by discussing mathematical models. A mathematical model is a mathematical representation of a real world situation. Instead of dealing directly with a complicated real world problem, we create equations or functions that describe the important relationship involved in the real world situation. So these models allows us to analyze a situation, explain how a system behaves, and predict future outcomes. Let's see the examples. For an example, businesses use models to estimate the profit. Banks use models to predict the loan payments. Engineers use models to design structures. So, the process of mathematical modeling consists of several steps to address these real world problems. So, let's see the first step. The first step, we wanted to identify the real world problem. As of the first step, we wanted to identify the real world problem. Next, we formulate a mathematical model. Then we solve the mathematical model. And after that, we have the solution of that mathematical model. So after that, we interpret the mathematical solution. Finally, we test whether the solution makes sense in the real world situation. If necessary, we revise the model and repeat the process. So, if necessary, we revise the model and repeat the process. Okay, this is how we can create the mathematical model. Okay, let's see the functions then. So next, we are going to discuss the functions. A function is one of the most important concepts in mathematics. So, a function is a rule that assigns exactly one output value to each input value. Simply, we can say that a function is a rule that assigns exactly one output value to each input value. So we often write y equals f of x or f of x equals y. Here x is called the independent variable. And y is the dependent variable. The dependent variable depends on the value chosen for the independent variable. Let's see the example of a function. Here, suppose we have f of x equals 2x plus 3. F of x equals 2x plus 3. If x equals 4, what happened? So if x equals 4, then the f of 4, substitute 4 into x, 2 times 4 plus 3, 11. So the function assigns the value of 11 to the input value 4. Function assigns the value of 11 to the input 4. Notice that every x value produces exactly one y value. So important note, every x value produces exactly one y value. That is what makes it a function. Okay, then let's say the range and the domain of a function. The range and the domain of the function. Okay. Okay. Domain and range. Okay. So when studying functions, two important concepts are domain and range. The domain is the set of all possible input values. Domain, the set of all possible input values. In other words, all allowable values of x. Right? Then, let's see the range. The range is the set of all possible output values. The set of all possible output values. These are the y values produced by the function. Y values produced by the function. Okay, let's see the example. For an example, consider a person's height as a function of age. Example, person's height as a function of age. Then what about the domain and what about the range? So the person height as a function of age. The domain should be all positive age values and the range would be the output values. That means the positive height measurements. So the range and the domain all positive ages, range positive height measurements. Right? Okay. I hope everything clear so far. Then let's move to the linear functions. Okay. So a linear function. I hope you remember the straight line equations. So a linear function is a x and y. In a linear function, we have x and y components, like in the form of the standard straight line equation. A linear equation in x and y has the general form ax plus by plus c equals 0. Ax plus by plus c equals 0, where a, b, c are constants and a, b are both not 0. More commonly, we write linear functions in slope-intercept form. I hope you remember that. The slope-intercept form, y equals mx plus b. On the other hand, we can define the function f of x equals mx plus b. Here m is the slope value, b is the y-intercept value. The major thing we wanted to remind, that is, a graph of a linear function is always a straight line. So the graph of a linear function is always a straight line. Okay, then let's move towards the real world application. So here you can see the example of the linear depreciation. So let's look at the example. A machine was purchased for $50,000 in year 2021 and will be depreciated linearly over 5 years to a scrap value of $5,000. So the decrease in value is called the depreciation. Decrease in value is called the depreciation. Since the depreciation is linear, the value decreases by the same amount every year. Okay, so let's say the starting value 50,000 in year 2021. After 5 years, the scrap value $5,000. So this decrease in value is called depreciation. Since the depreciation is linear, the value decreases by the same amount every year. Okay, then let's find the depreciation rate. Okay, find the depreciation rate. First, the initial value 50,000 in year 2021. After 5 years, final value 5,000, then the total decrease 50,000 minus 5,000, $45,000. over 5 years, $45,000. Therefore, 45,000, then divide by 5. Therefore, the machine loses $9,000 in value each year. The machine loses $9,000 in value each year. Okay, then let's create the model, right? Okay, create the linear model. So let's get that T represent year after 2021. Let T represent years after 2021. Then we know that we have T, and let's say the value of T, Vt. At the beginning, year 2021, when T equals 0, the value should be 50,000. After 5 years, when T equals 5, the value 5,000. Then we wanted to find the slope. This slope should be the value of depreciation, the rate of depreciation, negative 9,000. Negative 9,000. Okay, then V of t should be the linear function, the linear model. 50,000, the intercept value 50,000 minus 9,000 times t. So this is a linear function. Then let's find the value at end of year 2024. So let's find the value at end of 2024. So 2021, 2022, 2023, 2024. How many years passed after 2021? So 2024 is 3 years after 2021. 1, 2, 3. 2024 is 3 years after 2021. Then V of 3 equals 50,000 minus 9,000 times t equals 3. 50,000 minus 27,000. So the answer should be 23,000. That means the machine is worth $23,000 at the end of year 2024. So the machine is worth $23,000 at the end of 2024. This is how we can find out the linear function for the depreciation. This a linear function, a linear depreciation, the total value decrease over the time, the rate over the time. Okay, then let's move to the next example. The linear depreciation again. A company vehicle that has been original value of $25,000 will be depreciated linearly over 8 years with $5,000 scrap value. So let's get the information. Initial value $25,000. After 8 years, final value $5,000. Okay. Then rate of depreciation should be the slope value of t 8. Here we have 25,000 and 5,000. So 25,000 minus 5,000 over 0 minus 8. 20,000 over negative 8. What about the value? Negative $2,500. So let's write the linear function. V of t, 25,000, the initial value, minus 2,500 times t. Then by plugging the t value, you can find out the value of the machine or value of the vehicle at the time given here. Okay, then let's move to the linear cost, revenue and profit functions. I hope everything clear so far. Then move towards. So businesses usually have two types of cost. Fixed cost. First, the fixed cost. So the fixed costs are the cost do not change with production. Do not change with production. For an example, the rent, insurance and salaries. Also, the variable cost. These are the cost change with production. So what are the examples? Materials, labor cost, packaging cost. So the more units produced, the larger the variable cost become. Right? So when we produce more and more units, the variable cost becomes very large. Okay. Then we wanted to define the number of units produced and sold. Let's say X be the number of units produced and sold. X be the number of products or units produced and sold. So the cost function big C of X, the cost function big C of X should be, right, the total cost of producing X units. The total cost of producing X units. Then the revenue function would be the total money received from sales. So the total revenue from selling that X units. So let's say the total money received from sales. And the profit function, we know that profit means the total revenue minus the total cost. So revenue minus cost. Okay, then let's generalize the model for the cost function. Let's say we already know that the businesses or company, they have two cost components, the fixed and variable cost. Therefore, the total cost function, the cost function would be the combination of both fixed and variable cost. So the cost function C of x, okay, let's get a new page. Okay, C of x, cost function would be what? The sum of fixed cost and the variable cost, right? So therefore, let's take the cost per unit, C, and selling price per unit S, and the fixed cost S, F. Then the fixed cost remain unchanged, F, plus the variable cost should be number of units times the cost per unit, C times X. Therefore, the cost function F plus CX. The cost function. Okay, then let's go for the revenue function. The revenue function R of X should be the total money we earned by selling those X units. Selling price per unit is S times number of units, X, SX, R of X. Okay, then let's get the profit function. The profit function P of X should be the difference between the revenue and the cost, R of X minus C of X. Let's substitute R of X, SX, and the C of X, S plus CX. Then simplify, S minus CX minus F, profit function, right? So here is the general linear model for the profit function. Okay, let's move towards the example to get the idea behind the profit function, cost function, and revenue function. So this example says the green wave solar panels has fixed cost $15,000, cost per unit $25, and selling price per unit is $45. First, let X be the number of units produced and sold. Then here fixed cost 15,000, that is our uppercase letters F, $25 cost per unit, lowercase letter C, selling price per unit, lowercase letter S. Then cost function C of X, fixed cost plus C times X, 15,000 plus 25 times X. Revenue function R of X, S times X, 45X. Finally, the profit function P of X, the difference between R of x and C of x, 45x minus 15,000 plus 25x. 45 minus 25 x minus 15,000. 20x minus 15,000. Okay, this would be the idea behind the cost, revenue, and profit function. I hope no questions up to this point. If you have any question, feel free to email me. Then let's move forward. We wanted to discuss the demand and the supply. A demand function which relates the selling price to the quantity demanded. Typically, we write it as P equals f of x, where P is price, x is quantity demanded. Okay, so demand curves usually slope downwards because as price increases, customers buy fewer products. So, demand curves usually slope downward because as price increases, customers buy fewer products. And also, therefore, the demand function generally have negative slopes. Therefore, demand function generally have negative slopes, right? Okay, let's see the example. The quantity demanded of green tech solar panels is 60,000 units when unit price is 20. When unit price is 20, when price is $20, the quantity demanded X 60,000, and when the unit price is 30, the quantity demanded drops up to 40,000. When the price increases, customers buy fewer products. Therefore, when price is $30, the quantity demanded dropped up to 40,000. Right? Okay, now we have 2 points. The first point we have 60,000 and $20. Second one, 40,000 and $30. Okay, then let's find the slope. What about the slope value? 10 over negative 20,000, negative 0.005. So the negative slope confirms that demand decreases as price increases. The negative slope confirms that demand function decreases as price increases. Also, using point slope form, we can construct the demand equation. Now we know the slope and the 2 points. Okay, try it by yourself to get the linear function. Okay, then next consider the supply function. Let's move towards the supply function. A supply function which relates which relates the price to quantity supplied. So unlike the demand function, the supply curve generally increase because as the prices are rise, then producers are willing to supply more products into the market. Therefore, supply functions usually have positive slopes. Right? Okay. So as prices rise, producers are willing to supply more products. Therefore, supply function usually have positive slopes. Positive slopes. Let's see the example. The given supply function 3p minus 7x equals 1053. Let's solve for p. Notice that the slope is positive, therefore this is a supply function. Notice the slope is positive. Therefore, this is a supply function. If the unit price is 70, you can find out how many units will be marketed when the unit price is 70 by using this supply function. Substitute into the original equation and solve for x. This gives the quantity that producers will supply at that market price. Let's say, take one page. If the unit price is p equals 70, substitute into the original equation and solve for x. This gives the quantity that producers will supply at that market price. Okay, the original equation 3p minus 7x equals 1053. Substitute 70 here. Try it. Okay. So let's review what we learned today. So we discussed mathematical models, also functions, independent and dependent variables, domain and range, also linear functions, also linear depreciation, and cost, revenue, and profit function, demand functions, and supply functions. These ideas form the foundation for many applications of finite mathematics in business, economics, finance, and decision making. So, thank you for watching, and I will see you in the next section.